this guy here, which is our beta hat 2, 1, and so on. And the last element would be then beta hat n1, yeah, which is this guy here, which is here the estimate of the beta against the first risk factor of our nth asset. Yeah? So we grab always the corresponding element and stack it into a column vector, yeah, in this matrix denoted as B, capital B hat. We do the same for the second risk factor. Yeah? We grab all the corresponding elements that we have here in our vectors and stack it into this matrix here. So here it would be then obviously beta hat 1, 2, beta hat 2, 2, and so on. Finally, beta hat n2, yeah, which is this guy here. Yeah? We basically, because we get, of course, via OLS, we get 3 by 1 vectors. Yeah? So we have to extract the corresponding element, grab it from these vectors, and put it into this matrix here. It's easily done in MATLAB, and we will see that soon. Yeah? So, moreover, we add a vector of 1s here in our capital beta hat matrix, yeah? And so on. So our beta hat matrix here has obviously the dimension n, that's a n by 3 matrix. Yeah? And depending on the risk factors, yeah, it's always, if we have k risk factors, this matrix here has the dimension n by k plus 1. Yeah? In general, it's k plus 1. Yeah? Because we always add a column vector of 1s, the dimension is n by k plus 1. So that's the first step. Or actually, that is the first step. This is the second step here, defining our beta hat matrix. And the third step is now that we construct the vector of expected returns, which is very simple in this framework. So I will take this away now. Hopefully you have been doing your notes. So the third step in our cross-sectional Fama MacBeth regressions is we have to define a vector. I call it capital Y. Yeah? Capital Y, and what is that? Well, this is a n by 1 vector, obviously, where we have the sample average of our first vector. Y1 bar is our first entry. The second entry is the sample average Y2 bar from the second asset, and so on. And the last entry is yn bar, which is the sample average of our nth asset. And again, we operate with assets here in XS form, obviously. Yeah, that's how we define it here in our framework, and how it's usually defined in asset pricing or in finance contexts. Yeah. So, and what is yi bar? Yeah. So an I can be is 1 to capital N. It's defined simple as the sample average. So 1 over T sum from T is 1 to T, capital T, and then we have Y I T. So it's the cross-sectional, so this is the average return, the sample average return of our asset I. Yeah? Very simple. Let's take this away. This is our third step. And obviously we just need to program the code once. Once we have done that, so we can easily extend it to any asset universe, right? So the fourth step is now our second regression. So it's the cross-sectional regression. So let's denote lambda, or what we get is a vector lambda hat is defined as, surprise, surprise, we take our capital beta hat matrix that we defined earlier, transposed times itself, inverted times capital beta transposed times y. So in our case, we remember that's a n by 3 matrix, because it's transposed. This matrix becomes 3 by n. 3 by n. Beta is n by 3. Beta transposed is 3 by n. And our y, capital Y, is n by 1, right? So we know that these dimensions here must always match. So the column dimension of the matrix on the left must be equal with the row dimension from the matrix to the right. This is how matrix calculus works. So that's okay, that's okay, that's okay. And what comes out is obviously 3 by 1. Okay? So our lambda is obviously a 3 by 1 vector in our case, because we have two risk factors. K is 2, and the dimension of lambda is always k plus 1. So k plus 1 by 1, in order to be more specific. So what we get is lambda 0 hat, lambda 1 hat, and lambda 2 hat, obviously. So we get three numbers: lambda 0 hat, lambda 1 hat, lambda 2 hat. So what do we do with it? What does that mean? So the lambda 1 hat, that's the risk premium associated with the first risk factor, with our x1. Lambda 2 hat is the risk premium associated with our second risk factor. And now remember, what are we doing here? We regress the expected return, the average return, y, on the betas. So if we have a time series framework, so x transposed x, inverted x transposed y, so and we get our beta vector. So this basically answers the question, how does the variation in our regressor set impact the what is on the left hand side of the equation, so the returns. But now we have here average returns, expected returns, and we have here variation in betas. So how does the variation in our exposures measured by beta explain the average returns? How are the betas, how is the variation in betas related to the average returns? So it's a slightly different question that Fama MacBeth regressions answer. That's why our lambda vector gives us the risk premium. So whenever lambda 1 hat or lambda 2 hat respectively, if they are statistically significant, then we can say that the risk factor premium for the first or the second asset, that they matter, that the first risk factor is priced, and or that the second risk factor is priced. So we need to test if these guys here, are they positive? This is what we can just read here from what we get from the point estimate, so they should be positive, and they should be significant. If this is the case, then the risk premium rated or associated with the risk factor is priced. Moreover, what does our lambda 0 hat mean? So this is obviously the part, it measures the part of the average return, capital Y, that is unexplained by the variation in the betas. Okay? So that's the average mispricing, so to speak. So a weak test this is basically the counterpart to the joint tests of the alpha. You remember from previous lectures, in the seemingly unrelated regression framework, we tested the alphas jointly. When the alphas were jointly statistically significant, then we concluded that the factor model is not able to price our test assets correctly, right? Because it gives us basically the average, the alphas measure the mispricing for each asset respectively. But this lambda 0 hat, it gives us an estimate of the average mispricing, because it's related to capital Y, and this is the average return across our assets, of our asset vector. Yeah. So we have to test, so if this guy here is statistically different from 0, then obviously the beta exposures, or our model shows that it cannot price the cross-section of expected returns correctly. So this is a weak asset pricing test. There's also another test where we test the pricing errors, but this is something that we do not do here in this course. This is what people learn in doctoral level courses, okay? So now the question arises, how do we get the t statistics for our lambda vector? So that's now the question, and there are now many different obviously possibilities, how people proposed it in the literature, and you will read something like the Shanken correction, and so on and so forth. Because obviously the problem is that we operate here with estimates. Our regressor matrix here, our capital beta hat, this contains estimates from a previous regression. So there and any estimate is, they are random variables. So all of these guys are random variables. So this increases the degree of uncertainty here in this methodology, and that's why people figured out. Some people basically they use rolling window regressions. So what they do is, let's say we have here a timeline of from starting at t is 1, and they use, let's say, the first 60 months of observations, and they run the Fama MacBeth regressions and get the corresponding beta matrix and estimate the lambdas. So they get the lambdas for the first 60 months, then they roll this time window forward 1 month, take the next 60 months, and again estimate and get the lambda. And so they basically roll this time window forward until t. So they get basically, they have capital T minus 60 estimates for lambda. So in each run you can store the corresponding lambdas and then estimate the t statistic based upon the distribution of the corresponding lambdas, right? So this is not that difficult. This is actually pretty easy as well to implement in MATLAB. This is also something that I'm thinking about adding in this doctoral level course, which is also for you as master students, that I will teach next spring. So for those of you who are interested in these things, I highly recommend you to attend my next course. There you will learn much more sophisticated things. Yeah, we will learn resampling, sophisticated resampling, and you will be able to do very fancy econometric things, and you will have very sophisticated things that most doctoral students not even have, right? So, but this is not the approach, obviously, that I would like to talk here. We want to keep things a little bit more simple. We will take, the fifth step here is how to get the t statistics, the t statistics, for our lambdas. So what we do is we use this expression here. Yeah. So we use this whole expression here. Okay. And so let's write it here. Beta hat capital B transposed times capital B hat inverted times capital B hat transposed. Yeah, it's transposed. So times. So what we know is, okay, what is here? We need an n by 1 vector. Yeah, we need an n by 1 vector. So we multiply this guy simply with the excess return vectors, with the excess returns, with the cross-sectional excess returns at time t is 1. So